So, welcome to today's detector seminar, which will be on the cloud experiment. We are glad to have Eva Sommer with us, who is actually working on the cloud experiment since a while, doing her PhD on it. She's from Vienna and still finishing her PhD. And at the same time, she's a fellow here at CERN and acting as run coordinator for the cloud experiment. So well familiar with all the details. And the floor is yours, Eva. We look forward to your talk.
Okay, thank you. And thanks for the introduction. So yeah, I'm Eva, and today I want to talk about how we do atmospheric science at CERN at the cloud experiment. So a bit of change of topics probably to many talks that I've given you previously. But yeah, let me just introduce the cloud experiment to you. Now, being an experiment at CERN, of course, CLOUD is an acronym. And what CLOUD stands for is cosmics leaving outdoor droplets. So what this means is that overall, CLOUD studies how cosmic rays study the formation of aerosol particles, which then can act as cloud condensation nuclei to form clouds, which eventually have an impact on the global climate. And I will step you through all of these components and try and explain what we are doing here. So first of all, I want to start somewhere in the middle here. So I'm talking about cloud condensation nuclei. Now, cloud condensation nuclei are aerosols, and aerosol particles are essentially anything that is dissolved in air. I will go a bit in detail later, but first of all, I want to talk about this mechanism here. The most important thing that we should take away from this is that there is no single cloud droplet in our atmosphere that has not a cloud condensation nuclei at its core. So without aerosol particles for water vapor to condense on, we cannot form any clouds at all. Usually how clouds are formed is if we imagine a parcel of air that contains water vapor and aerosol particles. This parcel of air is at the surface at a certain temperature and at a certain dew point temperature. Now, as this air parcel rises in the atmosphere, the temperature and the pressure decrease, and the water vapor that is in this air parcel can condense on the aerosol particles that are inside. And this is how we form a cloud. Now, why is this important for a global climate? Now, if the average temperature on our planet's surface is always depends on the ratio of incoming solar radiation and outgoing solar radiation. So the amount of radiation that we receive on the sun on our surface essentially defines our global temperature. Now, clouds, as we all know, tend to be white. So when we have a lot of clouds in our atmosphere, especially on top of darker surfaces, these clouds tend to reflect radiation back into space. So they reduce the incoming solar radiation, overall cooling our planet. Now, again, as I said, clouds need these cloud condensation nuclei to form in the first place. But not only that, also the concentration of these cloud condensation nuclei has an impact on the kind of cloud that we make. So if we look at these two pictures here, and we imagine that we have the same amount of water vapor available to condense, but we have different amounts of seed particles that are available. To the left here, we would have a cloud that has fewer cloud condensation nuclei. And that means the cloud droplets tend to be bigger, and the cloud scatters less light back into space. To the right here, we have more cloud condensation nuclei, but the same amount of water vapor. So we have more smaller cloud droplets. That means that the cloud is more effective in backscattering radiation to space, but also that the clouds tend to live longer when they have fewer but smaller particles. So overall, all of this has an impact on our global climate. And as we know, we as humans have a big impact on the global climate as well. What you can see here is a depiction of various global radiative forcing agents. So those are different compounds that we as human beings have an effect on, which in turn have an effect on the global climate. And what these bars mean is the human impact on those compounds. So we know that carbon dioxide, for example, is the most important greenhouse gas. And we know that we as human beings have a big impact on the emissions of carbon dioxide. And we also know that it has a big warming effect. This is what this bar to the right here means, to the right. There are multiple other components. And then there's this blue bar here to the left, which in general means clouds or clouds and aerosol. And overall, as we just talked about with clouds backscattering radiation, we know that clouds have overall a cooling effect on our planet, but we don't know how much. Now also, all of these agents have a certain uncertainty associated with them. So we know that we have an impact on all of these. We know approximately the direction in which this impact goes, but for some of these components, we don't know how large our impact was. And overall, the total anthropogenic forcing on our global climate has this total uncertainty associated with it. And this largely or mainly comes from this unknown components that are clouds and the human impact on clouds and aerosol. Now, the reason for that is that if we look at carbon dioxide, for example, we know quite well. So whenever we talk about climate change, we compare our climate as it is right now to the pre-industrial climate. And we know quite well what the concentrations of carbon dioxide were in the atmosphere in the pre-industrial era, because we can measure that from ice core analysis and various other methods. However, we have no way of knowing how cloudy it was in the pre-industrial atmosphere or how many aerosols there were. So if we want to reduce this uncertainty and understand what our impact is, we need to model all of these processes. So we need to have global models that understand all the microphysical processes that lead to the formation of clouds and aerosol, so that we can then go back in time with our models and make an actual comparison. And this is the final aim of the cloud experiment, is to reduce this uncertainty and eventually reduce this one. So one aspect of aerosols that I just want to mention is aerosols are not only making clouds and cooling our climate, but aerosols are a very important air pollutant. Aerosols are small particles dissolved in air, and those particles, depending on their size and chemistry and various components, can reach into our lungs and even into our bloodstream. And those have a big effect on human health. And this is a very recent example from Delhi, from a recent smog event that's actually taking place right now. This picture is from a couple of days ago or weeks maybe, where we have, so the WHO recommends guidelines of how much of aerosol can be in the air before it has severe health effects. And this is usually measured in mass. So this is the mass of particles that are smaller than a certain size per cubic centimeter. And this should be, for a healthy environment, not exceed 5 microgram. However, here in this picture, you can see it exceeded 500. So this is another aspect of aerosol that we should not forget to talk about. But in any way, what are aerosols? And aerosols can have multiple different sources. What you can see here are primary aerosols. So those are aerosol particles that are directly emitted into our atmosphere. Those can have various shapes and sizes. So one of the most important ones is sand or dust. We're painfully aware viruses can be aerosol, as we all know since a couple of years. Sea salt is produced a lot in our atmosphere, is also very important. And this is soot produced by biomass burning or burning of fossil fuels. Pollen as well can be primary aerosol. But none of this is what concerns the cloud experiment at CERN. What we are concerned with are so-called secondary aerosol particles. Those are aerosol particles that are made in the atmosphere. So those are made from trace gas molecules that collide with each other and stick together and eventually form aerosol particles, which can eventually form cloud droplets. It is estimated that more than half of all cloud droplets in the sky originate from aerosol particles that are made from this process. And the process is called new particle formation or nucleation. So this is the process that we study at the cloud chamber. Now, the way it works is we have certain trace gas molecules, as I just said. Those are molecules, and some of them have a certain, so it's a statistical process. They just move around the air, and at some point they collide with each other. Depending on various factors, those molecules might stick together and add another one, and eventually form a cluster, which we usually define to be at around 1.7 nanometers. So at around this size, these clusters are more probable to stay in their clusters rather than to re-evaporate. And this is a formation that we call new particle formation. And so this process has, so various parameters are important for this process, this very early nucleation process. One of them is, of course, chemistry, so which kinds of molecules are those? And another very important aspect is the charged state of these molecules. So there are different mechanisms and everything depends on many, many things. But overall, when there is an ion or a charged molecule present in these early clusters, these ions tend to stabilize the cluster. So when we have a lot of ionization in our atmosphere, we tend to be more effective in forming aerosol particles this way, rather than we did not have any ions. Ions are usually made in our atmosphere by galactic cosmic rays, as well as also terrestrial radioactivity. And we at the CLOUD experiment, we study this exact process and the impact that it has. So we have a particle beam with which we simulate the impact of cosmic rays on this process. So overall, how does this happen? So usually what happens is we emit certain precursor vapors. Those precursor vapors, the most important one is SO2. I will talk about that first. SO2 is in our current atmosphere emitted by human activity to approximately 80%. So we make by far most of the SO2 in our atmosphere. SO2 is a volatile vapor. So SO2 on its own would not suddenly start to form aerosol particles. What happens in our atmosphere is that the SO2 is oxidized to form sulfuric acid. And sulfuric acid has a low volatility, and when two sulfuric acid molecules meet, they tend to stick together. So sulfuric acid is an effective nucleator to form aerosol particles, and then which then eventually grow to actual particles, from clusters to particles, and they can then eventually form cloud droplets. There are other components that have a similar mechanism. We will get to that in a bit. So the CLOUD experiment. What you can see here is a rather complicated picture of what our experiment is mainly, and we will step through a couple of these components just to explain what it does. But to start off, the most important part of the CLOUD experiment is, of course, the CLOUD chamber. Now, the CLOUD chamber is a stainless steel chamber that has a volume of 26 cubic meters, and it is the world's cleanest aerosol chamber. So what that means is that we can reach contaminant levels in our CLOUD chamber that are in the part per trillion volume range. So one molecule in a million other molecules is a contaminant here. So the reason we need this chamber to be so clean is because what we want to do in this chamber is to recreate true atmospheric conditions. So we want to recreate, we want to have air, inject certain trace gases, study the chemistry, and then watch as we make aerosol particles and observe how they behave. And in order to do that, we need to reach levels that are relevant for our actual atmosphere. And in our real atmosphere, the molecules that are responsible to form all of these aerosol particles, they do actually occur in these tiny concentrations. So this is kind of amazing to imagine that you have one sulfuric acid molecule and a million other molecules, and somehow they meet and they need another one, and somehow they form aerosol particles. And this is what we can simulate with this system. So for that, we have this aerosol chamber. It sits inside a thermal housing, so we can control the temperature of the aerosol chamber between -70 and +100 degrees with an accuracy of 0.1 degrees Celsius. We make the air that we put into our chamber ourselves. So we have two big dewars of liquid nitrogen and oxygen. And the reason for that is that we would not be able to filter ambient air down to these low contaminant concentrations. We have multiple light sources. Of course, we have a particle beam. This is a pion beam that we receive from the Proton Synchrotron to simulate the cosmic rays and create ions. We have mixing fans in our chamber, so that way, when we introduce the gases from the bottom, we can mix them inside our chamber so that we have uniform concentrations everywhere. We have a high voltage field, multiple instruments, and we can observe what's going on in this chamber in real time. I just want to look at a couple of components here. So one of the most important ones is of course our gas system. So this is a rather complicated picture, and this is just the overview. So we have multiple pages that look like this or similar. So what we have here is this is essentially an image of our chamber. And all of these various greenish little triangles and circles are different mechanical things that we can manipulate through the software here. So here in the very top, all of these, well, I don't know, triangle shaped things are valves. So we can open or close them to either let the flow go through or not let the flow go through. And those with the little circle next to it, those are mass flow controllers. So this very top one here is one of the most important ones. This is where our air comes from. So the main air that comes from the dewars, it's getting mixed inside our hull. And then it comes in here, and we can inject it into our cloud chamber through various paths. Another important thing I want to highlight here is here down below, we see another of these mass flow controllers that is currently being on. By the way, this is a screenshot that was taken yesterday. So this is a very current thing. So the experiment is currently ongoing. So here we inject air through this humidifier system, and that means that we can saturate the air to 100% with water. This is how we can control the humidity we have in the air in our chamber. This is a very important variable for all of the processes we study. And then down here, this little thing that doesn't look so important is another very important component. This is a lamp. And that means we can also make our own ozone in our system. So we inject pure oxygen into this line here. This is illuminated by this UV lamp, generating ozone. Ozone is a very important oxidant, and we can add this into our chamber as well. And this list of things here is the list of trace gases that we can add. So I mentioned SO2 in the beginning. I mentioned that there's a couple others. So anyway, the picture is a bit complicated, but we'll get there. So we can add all of these into our chamber as well at these very, very low concentrations that I mentioned before. So one of these, or the most important of these trace gases, is SO2. And this is another, again, if you click on that, you open this other page, and there are many, many pages like this. Look similar, we have the chamber here. SO2 comes from a gas bottle that contains a certain already rather low concentration of SO2. We have a system here with which we can dilute this concentration even further, and then inject it into this cloud chamber here. And another important part that I will get to in a bit is down here. We have a second system that we can directly inject our trace gases to, and this is our flow tube system. We will get into what this means in a bit. So what you can see here is also a picture that I took yesterday. This is the trace gas rack, or part of it. It's not complete, but some of our trace gases are in here. So as you can see, it is quite a complex system. Now, another important thing, as I said, are our light sources. Why? So what we want to do here is we want to recreate true atmospheric conditions. And if you want to recreate a true atmosphere, you need a sun. So what we have essentially are 6 different suns, so to speak, or six different light sources that emit light at different wavelengths. And the reason we need to do this is, as I said in the beginning, what happens in the real atmosphere is we emit these trace gases, or we emit precursor gases that are as such not able to form aerosol particles, but then some chemistry happens in the atmosphere, they get oxidized, and then they transform into low volatility gases that can make aerosol particles. And those chemical processes are often introduced by light. So we have all these different light sources. The one you can see at the very top here, so this is a picture taken from the bottom of the chamber when the lower cover was open, photographing up to the top. So at the top of the chamber, we have some Hamamatsu UV lamps that are guided through optical fibers, and we have hundreds of these feed-throughs so that we can uniformly illuminate the chamber with the UV radiation. Another important component are our lightsabers. So you can see one of them here, and here a picture of Serge illustrating why it's called a saber. We have 4 different ones of those that emit at different wavelengths. The newest edition is LS5, as you can see it down here. Anyway, they are numbered. This is a lamp that can emit very intense UV radiation, but not only that, it is divided into 4 sections. So we can also step the intensity of this lamp, which is very important to our experiment. What you can see at the bottom left here is we also have 2 cameras installed at our chamber, so we can actually look inside. In this case, what you can see at the very top here, so this is the top of the chamber. This little grid here is an electrode. I will get into that in a bit. And here you can see this little rod, and this is LS5 as it was being installed and turned on. Another important thing we can control at the cloud chamber is, of course, the ionization rate. So as I mentioned in the beginning, we receive a pion beam from the Proton Synchrotron. And you can see an illustration of this up here. So this is our experimental zone. We're located in East Hall. We received this beam, as I said, from the Proton Synchrotron after it hits the target. And then you can see this is our chamber here. And this yellow ray is our pion beam. Now, this is very different from probably all other CERN experiments because we don't have a high vacuum, super high energy beam line. In fact, what we are doing is we're defocusing our beam so that we irradiate a large fraction of the chamber simultaneously, which is then mixed through our mixing fans and so on. So with this, we can increase the amount of ions that we have in our chamber. We can even tune the intensity of the beam to mimic different altitudes in our atmosphere. Another important handle that we have on the ionization rate is our electric field. So as I mentioned before, this little grid is an electrode. We have a second one at the bottom of the chamber. And in between those electrodes, we can apply an electric field, which immediately removes all of the ions. So whenever we want to study the ion enhancement process of this nucleation rate, we always do that also in a neutral mode, meaning we remove all of the ions and see if we see a difference, essentially. Another important aspect are our sampling probes. You might have already seen it in this little picture before. So we are monitoring many, many different things at the same time. And we will get into that or what that means. But eventually what we have to do is we have to connect analyzing instruments to our chamber that in real time sucks the air from the chamber into the instrument and analyzes what's going on. And so this is a picture of a sampling probe as it is not installed. So this flange here is where it connects to the chamber. This stainless steel part here to the left is what penetrates inside the chamber. And here to the right, you can see a copper clad part. This is what would be outside the chamber, inside the thermal housing. Here you can see a picture of one of these probes being installed. Those are continuous tubes of stainless steel. So another important aspect of the cloud experiment and why we manage these low contamination rates is that everything inside our gas system and everything inside our chamber is only made of stainless steel or glass or ceramics. So there are no glues or adhesives or anything that could emit organics or any contaminants, which is quite a technical challenge, as you might imagine. Oh, how did I do that? Okay. This flow tube system, as I mentioned in the very beginning, this is another aspect that was newly added to our chamber. So this was installed 2 years ago. The flow tube system is essentially a quartz tube. We will see pictures in the next slides, which has its completely independent gas system and a completely independent temperature control. Now, the reason we want to have this flow tube system, so in the first place, the reason it was built and designed was the cloud chamber has one major disadvantage, as all aerosol chambers, as opposed to the real atmosphere, it has walls. So whenever a sticky molecule or an aerosol particle or a cluster or anything touches our walls, it's lost to the gas phase. It just sticks to the wall. In the real atmosphere, that's not what happens. We do, of course, have surfaces as well, but they're way, way less compared to the volume that we have. So trace gases and even aerosol particles can live in our atmosphere multiple days or even weeks. And this is something we cannot simulate in the cloud chamber because we lose the things within like a half an hour or something. So what we, so this is one of the ways to study more long-lived components in our atmosphere was to come up with this flow tube system. So the idea is to inject air and trace gases completely independently from cloud, add them into this flow tube system, and then age them in the flow tube before we put them into the chamber. Now, the way we would age trace gases in our atmosphere would be to expose them to high concentrations of OH. Now, OH is the most important oxidant in our atmosphere, and we can produce levels of OH in this flow tube system that are about 1e10 molecules per cubic centimeter, which would correspond to 10 days in our atmosphere. And we do that by using the system of UV lamps that are just outside the quartz tube, but inside the thermal housing of this flow tube system. We can operate all of them independently, and by that we can control the concentration of OH that we made. And then we can inject these aged vapors into the chamber. Now, so far we are still testing the aged or the aged trace gas aspect of the system. Again, it is very new. We have used it in 3 campaigns so far. But another thing that we have come up with 6 months ago was we are very, very good at making aerosol particles in this flow tube system as well. So again, if we inject our trace gases into the flow tube system and we oxidize them to make them sticky vapors, and those then form aerosol particles, we can inject these particles directly into the chamber, and we don't have to form them into our chamber. By that, we can vary the size of our aerosol particles that we want to inject very quickly, and we can also vary the chemical components that those are made out of. So the chemical we can inject aerosol particles of different chemical compositions and different sizes into our chamber to study them further. Now, those are a few pictures of this flow tube system and how it was being installed. This is maybe a bit complicated to see, but this is the ground floor of the cloud experiment. This is an air handling unit that moves the air around in the thermal housing of floaters and controls the temperature. Here you can see the quartz tube itself with one light. This is another picture of the tube itself. You can see this grid here is the ground. This is the first floor of our experiment. In order to install this long quartz tube, we had to remove parts of the floor here. And then very, very carefully, with a lot of sweat and tears, we constructed a pulley system so that we can pull up the flow tube and lower it down and insert it into its thermal housing. It was quite the operation. And amazingly, it worked. We did not break the glass. We did not destroy it in any way. It worked very well. Because again, here, this is part of our cloud gas system. So there's only quartz and metal. So we don't have anything that would be elastic or, yeah, it was quite the adventure.
Can you just point to the,
oh, I'm sorry.
To the flow to the picture?
Yes, so here you can see a glass tube and all of us like holding it and being very anxious. Here you can see the tube in the middle. And the reason this is blue is because we turned the lights on. So those are 1, 2, 3, 4, 5, 6 lamps. Yes. And this is it again, the quartz tube with 1 lamp. So another very, very cool feature of this flow tube is that we can make actual clouds in our cloud chamber with it. So as I said in the beginning, we are making aerosol particles or cloud condensation nuclei in this flow tube and inject them directly into the chamber, so that inside the chamber, we can then add a very humid flow from both the top, so from floaters, and the bottom, so from our main gas system. And what then happens is we create an actual cloud. And now this is something that we've just begun to study in this campaign, actually. So this is also a very recent image that was taken sometime in October, I believe. And here the chamber is at -50 degrees and we're making an ice cloud, actually. And this is very interesting to study because we can see often if you have trace gases in the atmosphere, those gases can be taken up or released by cloud droplets. The aerosols themselves can be transformed once they form a cloud droplet and then it re-evaporates. And there are multiple processes that we are hoping to study very, very soon. So another addition to our cloud experiment is charge 2. This is also very, very new. This is those experiments concerning charge 2 are actually happening right now as we speak. Charge 2 is a device that can produce multiply charged droplets or multiply charged aerosol. And the way it does this is, well, this is again a rather complicated picture, but you can imagine here, if I drew a line here, everything to the left of it would be inside the cloud chamber and everything to the right is outside. The main part of charge is this middle thing here. So these are 3 concentric tubes. The most important one being the one in the middle. This is a very narrow tube that ends in a capillary. We put a solution of very low concentration sulfuric acid into this middle tube and then apply a high voltage. And this in turn creates an electric field with field lines that are pulling outwards here at the very tip, which is already inside the cloud chamber. And by that, we can create an electrospray. So essentially we spray these liquid droplets of sulfuric acid that contain multiple charges. They contain multiple charges because the field is extremely high here at the top. And we have a syringe pump that always pumps very small amounts of liquid through this tube. And by that we can stably create multiply charged aerosol. Another thing that is important here is at the very tip of it, we have a radioactive source. Now, the reason we have the source here is that we can, so the middle tube is variable in its horizontal location. So we can either cover the source or expose it. If we expose the source, it means that we have very high concentrations of alpha particles here at the very tip where we make these multiply charged particles. And by that, we discharge them again. So we can study the same droplets that we make from this electrospray, either in their multiply charged state or in a neutral state. And this is, again, important to compare the properties and what the effect of multiple charges on these droplets has. Here you can see a picture of charge 2 being installed. You can't really see much because everything here is in high voltage. So obviously we have to be very careful and shield it. Yeah. So what would a typical measurement at our cloud chamber look like? Now, moving away from these specialized things like charge and these multiply charged aerosol, but this would be a very classic experiment where we study new particle formation. So this is, again, a very complicated plot, but I'll try and walk you through it. So at the very at the horizontal axis, in most of our plots that we show at Cloud, we have time. So time evolves as we go from left to right. And then we have multiple panels of multiple of the components that we have to monitor when we make an experiment at Cloud. At the very top are mainly chamber conditions. So this green line here would be our cleaning fields. This is the electric field we can apply that removes all of the ions. The purple line here is the aperture of this UV lamp that I said. So essentially, when this aperture is open, we have UV radiation in the chamber, and we don't if it's closed. Then the red line here is our pion beam. Now, in the next panel, we have sulfuric acid in purple, and then various clusters of sulfuric acid in the other colors. And at the very bottom, we have the concentration of small, very small aerosol particles. We have concentrations for different sizes. Usually we study the formation rates of particles at 1.7 nanometers, as I said, because this is where we define them to be stable-ish, at least. So what happens here is at the very beginning, we don't have any aerosol particles. We don't have any sulfuric acid, because what we do usually is we inject SO2, as I said, because this is what happens in the real atmosphere. We have a stable concentration of SO2 in the chamber, and once we turn on our UV light, this is this purple line that goes up, we can see sulfuric acid increase. And now one important thing about the cloud chamber also, as opposed to other chamber experiments, this is a steady state chamber. So we usually do all of our measurements in a steady state. That means we always want to produce as many gases and particles as we lose to the walls or by dilution and so on, so that we can get a stable data point. So we stabilize sulfuric acid here, and as we get an increased concentration of sulfuric acid, we see aerosol particles form. However, our field is still on. So the moment we turn the electric field off, we can see an increase in the particle number concentration here. Now, we don't have a beam on yet. So what happens here is that we see the effect of ground level cosmic rays, because obviously we're still getting rained on by cosmic rays all the time. The concentration is just way lower at ground level than it is at the top of the atmosphere. So here, if we have ground level cosmic rays, we can see an increase of the particle concentration already. And then as we turn on the pion beam, we can see that this really takes off. So essentially the quantities that we measure and that we usually report are these so-called J rates. So those are the formation rates of aerosol particles per cubic centimeter per second, and at a certain size. So we would usually talk about a J 1.7, which means this is a nucleation rate of aerosol particles or clusters at 1.7 nanometers. So in order to measure all of this, we need multiple different measurement devices. And this, I'm just giving a few very, very brief examples here to understand how complex the system can be. So if we want to measure aerosol particles and all of the aerosol particle size range that is relevant for our experiment, we need to monitor multiple orders of magnitudes. So what I tried here is I tried to make a PowerPoint slide where I actually scaled a circle by the amount that we would scale an aerosol particle. So this little tiny dot that is even smaller than my pointer, this would be an aerosol particle or a cluster that is probably not stable yet of 1 nanometer. Then we go bigger to 10, to 100, to 1 micrometer, to 10 micrometers. So in order to measure this entire size range, there is no one single instrument that could do that. And so we would need different kinds of instruments for the different types of aerosol that we want to look at. What you can see here at the bottom is a very, very typical plot for aerosol science in general. This is what is usually referred to as a banana plot. What it shows is, again, time on the horizontal axis, and then particle diameter in nanometers here on this vertical axis. And the color indicates the number concentration of these particles at a certain size at a certain time. So if we look at this plot from the very beginning, this is actually data that was taken at the cloud chamber, it's published in this paper, where a similar experiment was conducted as I've showed before. But this is now only looking at the particle size distribution. So in the very beginning, we can see blue everywhere. So there are no aerosol particles at any size. And as we move on in time and we change various components, like the gas phase, the beam, and so on, we start to produce aerosol particles at this low size range, and they grow over time. Now, if you really want to see it, those shapes look a bit like a banana. This is why it's called a banana plot. And this plot that I'm showing here is a combination already of 3 completely independent measurement instruments, because again, those span at least 2 orders of magnitude. But This is just to illustrate that we need many, many different kinds of instruments to measure, to get like the full picture of aerosol particles that we want to see. We can even measure cloud droplets, which are in this size range here. So one way to measure these aerosol particles would be, this is just an example, an SMPS, or a scanning mobility particle sizer. And these SMPS systems are used at cloud very frequently and in general in the aerosol community. But again, this is only one example. There are different methods to measure aerosol particles, and it very strongly depends on the size you want to look at and on other aspects. Now, the way these work is if we follow the aerosol particle here, it comes in here from the left. It goes into this long column, which is what we call a DMA, or a differential mobility analyzer. So what this DMA does is first of all, we need to charge our particle, or we can also look at the naturally charged particles. That depends on the kind of experiment you want to make and the kind of instrument you talk about. But the important part is that the particles need to be charged, and they need to have exactly one charge once they enter this DMA. And what this DMA does, it applies a voltage here in the middle. And as the aerosol particles come in, they have a sheath flow that is carrying them downwards, essentially to the exhaust. But as these particles are charged, they are attracted by this electrode here in the middle. And the amount of the path that they can take in this downwards going way that they are going through the DMA depends on the size of the particles, on their inertia. So this is how you can select particles of a certain size, is if you of course have to calibrate it, but if you know the voltage that you have at your DMA and you know the flow or the speed with which the particles travel here, I can select particles that are in a very narrow size range and that just pass through this little slit here at the bottom. And then I have selected an aerosol particle, but it is still too small to be detected on its own, especially if I'm talking about it just a couple of nanometers. So if we want to detect these aerosol particles, we put them into a so-called CPC, or a condensation particle counter. This is, again, only an example of how you can measure aerosol particles, but one that is used very, very frequently. So in this condensation particle counter, essentially what happens is these aerosols are grown. So we put them into an environment of supersaturation, where we have an excess of the most common vapor would be butanol, but you can use different chemicals. Again, depends on many things. So it would come into the supersaturated butanol environment so that it can be grown to a size where it can be detected by a laser system here. So this is an optical detector that grows particles that we grew before we put them into the system. Now, another very important type of instrument that is used a lot at the cloud chamber and by the aerosol society or aerosol community in general is a chemical ionization mass spectrometer. And so what this does essentially is it's a mass spectrometer. So we want to measure the gas phase, mainly particles, the gas phase molecules of those precursor vapors that eventually form aerosol particles. And if we think of how these mechanisms happen, so we start out with these precursor vapors that are usually often small molecules, they're very volatile, then we oxidize them, there's multiple chemical steps involved, and then we end up with longer molecules or with molecules that are very sticky and so on and so forth. So we need different kinds of mass spectrometers in order to get a full picture of the chemistry that's actually happening in our chamber. But in principle, the way it works is if we put a molecule in here and we get them into an environment of a reagent ion. So this is an ion that would react with the molecule and attach to this molecule and thereby charge it. And then we can put this charged molecule into this time of flight region here, where they just follow this electric field into the detector. And depending on the time it takes for them to take this flight path here, it's a similar principle. That depends on their mass. So this is how we can know the mass of these molecules once we charge them with a reagent ion. There are, of course, other types of mass spectrometers, and there is a very important one that does not use any charging at all, but just measures clusters or molecules that are naturally charged in our atmosphere. And we use a combination of all of these to get a complete picture of what's going on in the cloud chamber. So finally, this is what the chamber looks like. What you can see here is essentially the thermal housing. So our chamber is inside of that. As I said, the thermal housing is this thick layer of insulation. And inside the thermal housing, we have an airflow. We control the flow of this air and the temperature of the flow of the airflow. And thereby we can control the temperature of the chamber. So this is the chamber itself. There are multiple things surrounded here, and those are all of these different kinds of measurement instruments that I just hinted at. Cloud has multiple floors. So we have a ground floor that is below all of this. We've seen the floaters air handling unit sitting on the ground floor before. And we have steps here to go up to the top. Now, of course, doing all of this, we can't do that all on our own in our small team at CERN, but we're doing it in a cloud collaboration. So the cloud collaboration is a collaboration of approximately 20 research institutes distributed all over the world. This is also a recent picture that we took during our collaboration meeting. This is all, although I have to say this is far from complete. Many people attended online, and it was also at the very end of the workshop. So this is way more people than that, but this is the people that were present at the day we took the picture. So next slide. This is another picture of the same thing. We can see it here from the top. And you can see all of these instruments here labeled. So those are all different kinds of instruments that are connected. Again, we're at the end of our campaign, but we're still measuring. So we have approximately half of those still here, I would say. So we have multiple, you can see the flow tube system, not really. This is somehow behind this beam here. This elbow here is the return duct of the thermal air that is cooling or warming our chamber. And then we have various different kinds of instruments attached all around the chamber. Those metal plates, so you can see one here and maybe a little tiny bit of something here, those are our hodoscopes. So those measure the shape and intensity of our particle beam. And the particle beam is actually just going through the air here. So it is passing through these two metal plates. It's coming out of the edge of one of these concrete blocks over there and hitting our chamber. So this, of course, means that we cannot be in our zone once we turn the beam on. Or the other way around, we cannot turn the beam on as long as we're not sure that people aren't in the zone, because it would be very, very easy to just walk through the beam path and never know in this case. So all of these instruments that I've showed in the previous slide and that we've discussed so far, they're all sending data to our data acquisition system. And our data acquisition system then sends them to our databases, and we can display them in our control room in real time. So we have a time delay of approximately 30 seconds from what's going on in the chamber and what we see on these screens. And so this is what I have to say is really one of the coolest part of the cloud experiment. So we would make a change in the chamber, and then we would always, so we run 24/7 when we have a measurement campaign. So that means we have at least 2 people on shift in the control room, also right now, that are doing the actual experiments. They would change one thing and observe how this one thing changes another, for example. So we always try to make one change at a time and observe what's happening in the chamber. Do we form particles or don't we? Or do we form them less or more? Or what's the chemistry that's happening? So in reality, we spend a lot of time like this, staring at these plots and solving puzzles. And this is really, really nice. So you would do make one change, try and find out what went wrong, for example. Why is this not working? Or is it a discovery? Is it a problem with an instrument? We've had all of these cases multiple times. So this is really, really a nice collaboration. Then of course, sometimes in between experiments, we have to clean the chamber as well. So whenever we have high concentrations of trace gases, and we want to have different trace gases, for example, we need to get rid of the old ones, then sometimes in between experiments, we have to make long temperature transitions. So this, when we want to go from plus 30 degrees to minus 50 degrees, this takes almost a day, for example, because it's a big system, and in order to cool everything down. So we're not always this serious. Sometimes we have wait times, and we can have a little bit of fun in the control room as well. So a brief overview of what the cloud experiment has shown so far. So what I'm showing here is the picture of what it looked like before the cloud experiment has started, and in 2010 approximately. So I kept talking a lot about SO2 and sulfuric acid, and how sulfuric acid is very important to form aerosol particles. In fact, for a long time, it was believed that sulfuric acid is necessary to form any aerosol particle. So what people would do is they would go out and take measurements of the sulfuric acid concentration and the nucleation rates, or the rates of aerosol particle formation. And then eventually this was the picture. So as we increase sulfuric acid, we increase the formation rate of aerosol particles, yes, but there is this big scatter, and it wasn't quite understood why or what exactly is going on. Now, ever since the cloud experiment has started, the picture has changed. So what we can see here is the same data depicted in these faint dots here. And then first I want to direct you towards this gray line here. So this was one of the first experiment, or the first experiment maybe, that was conducted at the CLOUD experiment. That was the nucleation rate of sulfuric acid, because this is what people thought was driving all of this. And what they found was that you need way more sulfuric acid to reproduce the same nucleation rates than was observed in the atmosphere. Or put the other way, having only sulfuric acid would never reach these nucleation rates that were actually observed. So what is the truth, or what we know now, is that not a single one of these data points that we see up here is nucleation of pure sulfuric acid. But there are multiple other components that are very important in taking part of this. So they're either very important as stabilizing this nucleation rates of sulfuric acid, or they're even components that can nucleate on their own completely without sulfuric acid. So for example, this red line that we can see here at the top is sulfuric acid with BMA. So this is dimethylamine. This is a very important component, especially in urban regions, where we see that there are very, very fast nucleation rates at the kinetic limit. So that means it's only limited by the collision rates of sulfuric acid molecules once we add this component to it. And there are many other components that are important to this. So one of the results, this was already some time ago, but this is again sulfuric acid. And here we were looking at the temperature dependence of so yeah, all of the things I showed before were at the same temperature and in the boundary layer. But what we were looking at here was the effect of temperature and the effect of ionization rates on the nucleation rates of sulfuric acid. So you can see 3 different colored lines here, which correspond to 3 different temperatures. And all of these different shades correspond to different ionization rates. And we can see that the nucleation rates of sulfuric acid is strongly enhanced, but it all depends on concentration and temperature as well. So the picture is way more complicated than it was thought at the very, very beginning. Another important result from the CLOUD experiment was the nucleation of pure organic molecules. So again, in the beginning, it was believed that we need sulfuric acid always when we want to nucleate aerosol particles. But here it was shown, there were theories before, but it was shown at CLOUD for the first time that oxygenated organic molecules can nucleate completely without sulfuric acid. And so there was no sulfuric acid in the chambers. We increased this concentration of oxygenated organic molecules. We increased the nucleation rate. And another important effect that was observed in this experiment was that the presence of ions increases this nucleation rate by a lot. So all of the dots we can see here are neutral nucleation rates, so with the field on, and all of these triangles are in the presence of ions. This is especially important for the pre-industrial atmosphere when we had more wooded areas. So those oxygenated organic molecules, as I said, they are organic. They come from emission from trees and vegetation all over the world, and are very important, especially in non-polluted environments. Then another component that was measured at the CLOUD chamber is iodine, or iodic acid. So it was also shown that iodic acid can nucleate and form aerosol particles completely without sulfuric acid. However, it is strongly enhanced by its presence. Here we see, again, a very similar plot, iodic acid here, the nucleation rate here, and different conditions. So we have different temperatures here in blue and in red. And the symbols correspond to different ionization rates. So the circles would mean we have no ions, enhanced ions, and then ions from the beam. And we can also see a strong dependence on the presence of ions here, but it depends strongly on temperature as well. So overall, the CLOUD experiment has shown that this picture is way more complicated than it was thought in the very beginning. And this is from a recent paper that just came out last year that summarizes all the results that CLOUD has produced in the past 10, 14 years of operation. And so essentially what it shows is that there is not only sulfuric acid or sulfur dioxide as this precursor vapor, but there are many others. So if we look at this picture here, all the yellow components here are the volatile precursor vapors. Again, those are emitted into our atmosphere and they are then oxidized to different components. So we can see iodine here, dimethyl sulfide is an important one. Sulfur dioxide, again, we know it's very important, but not the only one. And then all kinds of organic vapors, biogenic organic vapors, or anthropogenic ones. And those nucleate to form, or sorry, those are oxidized in the atmosphere to form those nucleating vapors. And all of this is strongly enhanced by certain stabilizers. So an important one is, of course, ions, but there are others like ammonia amines, as we've already mentioned in the beginning. And those nucleating vapors then eventually form aerosol particles, which do have an impact on smog production, and of course on cloud condensation nuclei as well, which in turn has a strong influence on our global climate. So with that, I would like to thank you, and any questions are welcome.
Yeah, thank you very much, Eva, for the very didactic talk, and was even easy to follow for those who are not meteorologists or atmospheric physicists. Who has a question? Yes, please. Give you the mic.
Yes, I have thank you for your talk. I have a question about slide 20, where you showed the graphs. Yes. So these other molecules, let's say the blue, green, and red lines, do you add these, or do they just form once you turn off the high voltage?
Yeah. Sorry, I probably didn't. So
Okay.
those form. So okay, those are measured in a mass spectrometer that does not actually have a charger attached. If I remember, yeah, I'm pretty sure. So this instrument can only measure naturally charged clusters. And so those can only be seen in the instrument once we turn the field off. And so, yeah, it is sulfuric acid with more sulfuric acid, essentially.
Thank you.
We have some questions also on Zoom. We start with Gianluca, please.
Oh, yes, good morning. Thank you very much for your detailed, very interesting presentation. You presented us many detailed results, basically showing, if I understood correctly, that there is an enhancement on the formation of CNN depending on the cosmic ray flux. But this depends very much on the temperature, on the cleanliness of the atmosphere, and so on. So exactly. Now, I know the question is going to be very difficult, but it basically is the question why this experiment has been thought. There are observations from the past, and I refer also to 1,000 years ago, from stalagmites, that basically seem to show a dependence on Earth temperature depending on cosmic ray flux. And there are also models nowadays, they try to correlate the temperature increase on our planet or modulation on cosmic ray flux. Now, did you try to put, yes, this is a very complex image. Did you try to put all your detailed and complex results into a global circulation model to check the real effect, the measurable effect of cosmic rays on possible temperature on Earth?
Absolutely. So I think what we know is that ions, or cosmic rays, do have a stabilizing effect. But as you just said, not only that, it depends on many, many things, and not only the concentrations of ions. So by now, we cannot say that we have proved this. That quite the opposite, I would say. I think we know that in our current environment, we have so many components that are way more effective as acting as stabilizers than ions, that in our current atmosphere, this is not so important. About the pre-industrial atmosphere, I'm not sure how well understood this is yet. And yes, we do work very, very closely with modelers as well. So modeling groups are a very active part of Cloud. And all of the results that you can see here are eventually put into global models. We have only recently, a paper was published that incorporated the effect of ammonia on the atoll layer. So yes, all of this is incorporated in models as well. Of course, it takes time, but yeah, we're working on that. So eventually, we would like to have this complete picture and be able to have a complete global model. Yes.
Okay, thank you.
And
Okay.
maybe I should clarify, I'm not claiming that cosmic rays have an effect on our global climate in our current atmosphere. I think we have shown that this is in the current atmosphere not so important. All of these other components take part as well.
Okay, then we have a question by Greg Hallowell. Please.
Yeah, hi, thank you for a fascinating talk. I have a question which may be a little bit tangential, and I was wondering whether a device like CLOUD could be used to monitor atmospheric lifetimes of certain molecules. For example, there are restrictions coming in on PFAs, fluorinated compounds, and there are some compounds where some fluorines are replaced by oxygen, and these molecules are said to have shorter atmospheric lifetime because they're broken up more easily by 300 nanometer photons in the upper atmosphere. And I was wondering whether, but the lifetime of these molecules is very dependent on their molecular structure. You can have different isomers which have long lifetimes and others which have short lifetimes. So it's all in the placement of the atoms, particularly the oxygen. I was wondering whether CLOUD, an instrument like CLOUD, could shed some light on what the GWP20 limits would be for some of these molecules. Would it be a big change from what CLOUD does now and the analysis capabilities?
I think that would depend on the lifetime we would expect of those, because so the lifetime of everything in CLOUD is limited. First of all, so CLOUD is a stable state reactor. So we always add an amount of trace gas and we take away an amount of air. So you always have a constant flow of gases in and gases out. The gases are taken out by the instruments and of course also by our exhaust system. So we have a so-called dilution lifetime that is limiting studies like that. And then also the walls, of course. So if any of those molecules would stick to the walls, those would pose a limit to these possible lifetime studies as well. So I'm not sure if the lifetime is within minutes, then maybe, but yeah.
I was just thinking, is CLOUD very different from the kind of apparatus you would need to be able to measure the atmospheric lifetime of molecules from the global warming perspective, CO2 perspective?
Yeah,
in terms of CO2 equivalent lifetime.
I do believe that it is different from an apparatus that you would need to do that, mainly because of this, because of its limited lifetime of everything in the chamber, because we're constantly taking gases out and adding gases. So we're having a stable state of what we add and what we take away.
Okay.
And that just limits the lifetime of whatever we could look at.
Okay, well, thank you. Thank you very much.
Yes, and we have a question of Herman Kolanowski. Please, Herman.
Hello, thank you very much. A very interesting talk. You're using ionizing beams, which are probably going through your chamber, right?
Sorry?
I mean, cosmic rays, we know they form showers. And
Yes.
in the showers, there are particles which are ranging out.
Yes.
Ranging out means that you have then very localized clusters of ionization. Have you considered that, or could this change or influence the picture? Probably not change, but influence the picture.
If we had clusters, you mean?
I mean, very dense ionization, like in Bragg peaks from hadrons.
I'm not sure. So what we receive is a pion beam. So the beam itself is pulsed, which is not exactly the same as it happens in the atmosphere, right? So it's,
yeah.
And this we see. So we have instruments that have a high enough time resolution so that we can actually see these pulses. We try to mix them in the chamber as uniformly as possible. We do have studies on these ion-ion recombination rates. This is one important thing that we do study and we investigate. So depending on depending on the temperature, so I'm not an expert on this, but depending on the temperature, I believe, and depending on the intensity of the beam, we do see different recombination rates of these ion pairs that we produce in the chamber. So yeah, probably, yeah.
Yeah,
Actually, I'm not sure if it's so different, because what we receive are pions, and this is also what's mainly ionizing radiation in the atmosphere as well. So
yeah, but I mean, I think there's a difference between a through-going beam like the pi minus, I think you have, and a shower with a lot of particles which are finally, or at least some of them are ranging out in the atmosphere, in the part where the weather really forms.
So we are defocusing the beam, and we are trying to irradiate as much of the chamber as possible. So by that, I think it is approximately a third that we consider into this hot region where the beam actually passes through. So it's not like we have this narrow beam line, but it is diverging. So
that's what I mean. I mean,
okay,
I'm considering the application of hadron beams, for example, for tumor treatment, and there it really depends on the density of ionization to treat this, and so this is just the picture which I'm thinking of. And if you have instead of an through-going pion beam, if you have then something which is ranging out, then this makes just denser localized ionization, which could affect the forming of aerosols finally.
Maybe I can just say to the same comment, but I think I get the point of the comment, and that might be valid. And maybe the proposal would be that can you put a secondary target in order to make your pion beam shower? The problem here and the issue is that the pion beam, indeed, it goes through. You have a very low probability that it interacts somewhere and it showers. And the question he's asking is that if you have really low energy particles, secondary particles produced by the pion beam, they are going to stop. And if they stop, you get the Bragg peak, which means that you have in very small volume, a very high ionization. And the question then is this affecting your nucleation? Because you have much more ionization in a small volume than what you get produced with the pion beam. Mm-hmm. It actually goes in the other direction that you said, that you defocus the pion beam. If you would have focused it, it might be closer to these Bragg peak effects, but the Bragg peak is so intense that you really have a small volume, a lot of ionization. And that was the question, if this changes anything.
Okay. Well, to be honest, I'm not so sure. I mean, we have, whenever we report a nucleation rate and its dependence on ionization rates, we usually do that in these three steps, right? So when we have the field on, then when we have no beam, and then we have the beam on. And then there is actually another step behind this, which would be PS has died. So when the proton synchrotron is completely off, we do see a difference in the ionization rate in our chamber, just because of there's no more scattered muons. So yeah, not sure.
But this, I thought this pion beam is to simulate the situation in the higher atmosphere, right? And yes. Therefore there shouldn't be stopping the pions if they come down to the surface. So I don't think it's a big effect.
Yeah, okay. I agree with that. And can I ask my question, or do we have to go?
No, you can ask your question. Then we have afterwards a question in the room, please.
Thank you. So Eva, thank you very much for showing what Cloud has achieved throughout its history. I mean, I still remember in 2006 where temperature control was not great, and things would just spontaneously nucleate. So there's been a lot of evolution in terms of controlling the atmosphere inside the chamber and the temperature, and building your own air so that it's actually completely pure. I wanted to ask you if there have been changes in the requirements, for instance, to time in the different sub-detectors, let's call them like that, the different instruments. Because as you said, you have instruments that are very fast. You have others which have a different kind of time resolution. Has this evolved? What are the requirements now?
So we do, in theory, sync all of our instruments to a common clock. This is all part of our data acquisition system. And however, of course, it depends on the kind of experiment you make. In many cases, like these graphs that I showed, we don't need a very high time resolution to measure this. So here it is usually fine to just be sure that all of these are synced, sort of. But if you would measure something like ion-ion recombination rates, then of course you need a different time scale. But yeah,
okay, so among instruments, you are still on the order of a millisecond is good for everything. Is that
absolutely?
Okay, great. Thank you.
Yeah, then we have one more question in the room, please.
I wanted to ask a question, maybe going back to the particles that you're using. Obviously, the way that you talked about using pions is just a ionization source, which I think is like very good for your studies. I was wondering if there's any case to try to see effects of maybe protons, even in the higher parts of the atmosphere, if that might be a plan for the future for cloud.
I mean, eventually what we care about is the concentration of ions. And so, period. So I think, and also this is very representative for what's actually happening in the atmosphere to use pions. But if the effect that was asked about before is a very big thing, then maybe that would be a difference, but I'm not sure. So as far as I know, what we do care is the concentration of ions, and this is what we achieve with this as well.
All right, thank you.
Yes, please.
I would have two technical questions. I think they will be rather short. The first one is that you said that you use dilute gas, so for instance, the SO2 from the bottles. How are you sure that the gas mixture, if the bottle has been standing there for a long time, is still uniform? Do you have to shake the bottle, or what are you doing there?
Well, what we eventually do is we trust our measurement. So whenever we
are measuring it.
Yes.
Yeah, okay.
Whenever we set these mass flow controllers in our gas system and we want to achieve a certain concentration of something, we do of course have a way to calculate that, and this is what we set, and it usually ends up to be something else, because especially even the accuracy of these bottles, even if they are fresh, is not very high. So yeah, we always have to just trust what we see.
Okay, and the other one would be that you said that you have to clean the chamber, which is very understandable. How are you doing it? Is it a bake-out system, or what are you?
So there are different ways. If we want to make a very fast cleaning, so if we're not changing very much with the chemical system, but we just want to reduce the concentrations of both particles and trace vapors, what we would do is we would increase the speed of our mixing fans. So we have these two fans at the top and the bottom, and they just mix whatever is in the chamber. And when we turn them to full speed, we increase the turbulences that we have in the chamber, and we essentially throw stuff to the walls. This is how we get rid of things in the gas phase. We make use of our wall loss rate. This is a fast cleaning that you could do within an experiment. However, at some point, when you throw a lot of things to the walls, at some point it will come back, especially if you change temperatures or chemical systems or whatnot.
My question was, how do you clean the walls if you have to clean the
walls?
Yes,
in this case, we would need to do two things. We can heat up the chamber. As I said, we can go to 100 degrees. We can have very high flows through the chamber. And then if even that doesn't help, we are doing a so-called Karcher cleaning. So we have a device that we can insert into the chamber, and it essentially sprinkles ultra pure water all over the walls. And we do that like a dishwasher. We do that for 24 hours. And then we heat the chamber up to, under very humid conditions, to 100 degrees. And this essentially clears everything. However, I also want to add that we are very careful in terms of contaminants. So we always run this chamber at a slight over atmospheric pressure so that nothing can get in from East Hall. And even when we don't run experiments, we always keep it that way so that we don't get too many contaminants from outside.
Okay, I would also have still two brief questions regarding the new elements you have Lotus, and also charge 2 you mentioned. You are fully satisfied already with the performance?
Well, I would say both is a work in, like charge is literally a work in progress that's happening right now. And we could already see that it's performing very well. And so we have already taken data that is really nice with multiply charged particles that we directly emit from the charge system, but we also were able to multiply charge larger particles that we injected from the flow tube system. So this is already quite good, but of course experiments are going on.
Yeah.
And Floatus itself is such a big and complicated device that some aspects of it are working extremely well, like this production of cloud condensation nuclei and so on. Other aspects of it are still very much work in progress, but we are still exploring this big system and yeah, working on things.
Okay. And my other question is, if you go back to one of your very early slides, I think slide 3 or something like that, where you showed not this one, sorry, no, a bit further down. Next one, maybe. Yes, here. You show there actually the change in effective radiative forcing from 1750 to 2019. And you said one of the aims of cloud is to reduce the uncertainty on the aerosol cloud or whatever aerosol radiation, the two elements you have there. Now the error bar here is indeed very large. I suppose this was before cloud started?
No.
No.
This is actually very recent. This image is from 2021.
Okay.
However, again, we are working closely with modeling groups and they are incorporating cloud results. But this picture, even the complicated one I show at the end, is just far from complete.
Okay.
So there are still many things that we do not understand.
Okay. So my question actually is, compared to the time before cloud, how much could you get down the uncertainty, roughly speaking?
Well, to be honest, I don't know that answer. I know that there are global models that are incorporating results from cloud already, but this is ongoing work. This takes a long time.
Okay. Yeah, thank you again for your very nice talk. I think we answered, we had all the questions, nothing left on Zoom. So thank you again for coming also. It was very good attendance. The next